Okay, so in this station, we're going to be talking about compound formation. And in order to do that, first we're going to discuss the different types of bonds that we learned last year in K chemistry. Hopefully, you'll remember some of the basics about these main bond types. So the three main types of bonds that we talked about were ionic, covalent, and metallic. And what you may remember most prominently is the type of elements that make them up. So bear with me, I'm writing on my screen. So for ionic compounds, you may remember that they form between metals and nonmetals. You may remember that in ionic compounds, I'm forming between something that is very electronegative with something that is non-electronegative. We talked about electronegativity being kind of a popularity with electrons, which means that for an ionic compound, it's very easy for the very electronegative atom, for example, fluorine or chloride, generally the halogens, to steal the electrons away from something that's very non-electronegative, something like alkaline earth metals or alkali metals. So some other things that we have talked about with ionic compounds is that because of the large electronegativity difference, we have a stealing of electrons. Right, so we don't share electrons. We have a complete transfer of electrons from one element or polyatomic ion to the other. Some other things that we know about ionic compounds is that, again, they have that large electronegativity difference. Right, that's why we generally have something from the left side of the periodic table that's very not electronegative pairing with something from the right side, which is very electronegative. In general, and of course we talked about solubility at the end of the year, but in general, these ionic compounds are soluble in water, so they make those aqueous solutions. And when they do dissolve in water, they become what are called electrolytes, which means that they can conduct electricity as a solution. In contrast, covalent compounds are formed between more similar atoms. So these are going to be between nonmetals and nonmetals. And because they're both nonmetals, they have a very small electronegativity difference. And there are different cutoffs based on who you ask about what constitutes a small electronegativity difference. We're not going to really focus on that. They have a small electronegativity difference. And because of that small electronegativity difference, there's not enough energy to really steal the electrons. So instead of stealing them, we're going to share our electrons. Covalent compounds, also sometimes known as molecular compounds, they can be soluble in solution. So I'm not going to speak to whether or not they're soluble in water because some are soluble, some are not, depending on whether or not they're polar or nonpolar. But they never conduct electricity. Right, so they are not conductors of electricity, they're actually good insulators. Again, I apologize for my handwriting, I'm using my finger. Alright, and finally, we didn't focus too much on metallic compounds, but metallic compounds are formed between a metal and a metal. And you may remember that because of the nature of metals, they have this very loose association with their electrons. So we describe them as having this sea of delocalized electrons. And this sea of delocalized electrons means that no metal atom is specifically holding on to his electrons. They just kind of float above them. And this makes them excellent conductors of electricity, both in the solid state and the liquid state. And notice that I'm saying liquid here and not solution. So I'm not talking about dissolved in water. I'm talking about if I physically take that solid and I melt it, it's going to be a good conductor of electricity. So they conduct as solid and liquid. Sometimes you may hear people say molten. Okay, so in order to look at ionic compounds, we need to brush up on our terminology. So we have two different types of ions. We have anions and cations, and both of these different charged species of atoms are going to occur when an electron is transferred from one atom, from one element to another. So for example, as far as anions, That's going to be our negatively charged ions. And these are going to occur when I get more electrons, so when I pick up electrons. So this will happen for something that is an electronegative atom. So something like chlorine, for example, tends to pick up one electron from another element, and when it does so, it becomes a negatively charged ion, Cl-, and we call it chloride. The way that I tell people to remember anions are negative is that an starts with an, like ants, and nobody likes ants. Okay, so anions are negative. They form when I pick up, so I gain an electron. And the more electrons I gain, the more negative I become. In contrast, cations are positive, and one way to remember that is that cats have paws. So cat paws. This is going to occur when I give away an electron, so something like sodium. Sodium tends to give away an electron. When it loses that negative charge, it becomes positively charged. For every electron I give away, I'm going to become more and more positive. So something like magnesium, which gives away 2 electrons, is going to become Mg plus 2. Okay, so this is something that a lot of people struggled with, which was energy levels, but it's really important to understand the location of the electrons within an atom in order to understand the chemistry that that atom is going to participate in. So the energy levels, you'll remember, correspond to the periods on the periodic table, and I'm briefly going to review just how I get the electron configuration from these energy levels. So let's look at magnesium first. So in order to get to magnesium, I have to go through all the other elements that come before it. So in the first energy level, I'm going to have 2 electrons, and those are both s orbitals. So it's 1 s2, and we'll go into this in much more detail later in the semester. I'm just doing a quick review here. Then I'm going to go to the second period, which again, it corresponds to the second principal energy level. I have 2 orbitals in the 2 electrons in the s orbital. So that's going to be 2, they're s orbitals, and there's 2 electrons there. Then I have to go through all 6 of the p orbitals. So in the second principal energy level, I have p6. Again, that's 6 electrons in my p orbital. And then I go to the third principal energy level, 3. Again, I'm in the s box, so s orbitals, and there's 2 of them. So 2. So the electron configuration for magnesium is 1s2, 2s2, 2p6, 3s2. And again, we'll go through this in more detail at a later date. These energy levels allow us to make what's called a Bohr diagram, which shows us the general arrangement of all of the electrons within the atom. So for a Bohr diagram, I would write magnesium. I would show in his first orbital, he has 2 electrons. That's my 1s2. Then his second, he has 2s2. Then he has his p orbital, and he has 6. So 1, 2, 3, 4, 5, 6 electrons in his p orbital. And then his outermost orbital is his 3s orbital, and he has 2 electrons there. So we know that it's these outermost electrons, which we call the valence electrons, that are going to be the most important for chemical bonding. So in a Lewis diagram, we focus only on the outermost shell, which has these electrons called the valence electrons. So the Lewis diagram for magnesium would be Mg 1, 2. Okay, so what is the point of focusing on these Lewis diagrams? Well, they allow us to predict the compounds that are going to be formed from these elements. So here, for example, I have 2 different Lewis diagrams, one for sodium and one for chlorine. And notice again that we're only looking at the valence electrons, so the electrons in the outermost shell. So for example, for sodium, sodium's outermost shell would be 3s1. So I'm looking at that 1 electron in the third principal energy level, whereas chlorine would have 3s2, 3p5, yes, and 5 plus 2 is 7, which gives me his 7 valence electrons that we're looking at. So I had to double check my math because, math is hard.